Well, it turns out that for ideal gases, if they're at the same temperature and pressure, then the molecules are equally spaced. And if they're equally spaced out, that means that equal volumes have equal numbers of molecules. So it doesn't matter how big these particles are, the space between them is considered the same. This comes out of the fact that the ideal gas law treats particles as though they're point particles. They don't have any volume. So this is a pretty good assumption if the molecules are really small compared to the space between them. By the way, this is a law called Avogadro's law. Avogadro's law says exactly this. Equal volumes at the same temperature and pressure have equal numbers of molecules. So I like to think of it this way about their equal spacing. That helps me come up with some reasoning and predictions. But note that even though the number of particles is the same, the mass of the particles can still be different, because certainly these molecules have more mass. And if the mass is different and the volume is the same, then the density can be different as well. In fact, I would say that the density depends directly on the mass of those particles. Let's consider hydrogen and helium. And the hydrogen is actually diatomic and it's not shown here, but let's pretend. And I put their molar masses down here, and we can see that helium has twice the mass. So these, at the same temperature and pressure, the spacing's the same. So we have the same number of molecules in each volume, so same volume. But the helium, it has twice the mass. So that means that the helium will be twice as dense. So this can come in handy because you can compare the density of two gases just by looking at their molar masses. And so, for example, if I'm comparing the fluorine and chlorine gases, I can just look at the periodic table and I don't even have to calculate the molar mass. I know that the fluorine has a lower molar mass, so it will be less dense, and chlorine will be more dense. Because it has a higher molar mass. So that can be convenient for deciding, like, if a gas is going to accumulate at the ceiling because it has a lower molar mass than the average molar mass for air, or if it's going to sink and travel along the floor. Okay, so one thing that we can do, we can actually solve for density, and this equation can be used to do that. This equation is derived from PV equals nRT, our ideal gas law, and it was derived by plugging in mass over molar mass in place of N for moles, and then rearranging.